to be here. Do we have lights, camera? Okay, I'm thrilled to be in Corsica and meeting all of you. I have a very fond view of Corsica from an early age. When I was 11, I came on sabbatical with my parents to France, and I remember my first day of school was pretty rough because I didn't really understand French, and worse than that, they made me take German and Latin in French, and so I was really pretty confused by the end of the day. And then the teacher sent us to the library, and we were told we could read anything we wanted, but it had to be, but all the Astérix were not in French. So of course I went straight for the English, and it was Astérix in Corse. So I felt like I've always felt that it was like, a rubber tube being given to someone who was having trouble swimming. And that cheered me up again, and here I am. So anyway, I've been coming to these schools since 1991. And in fact, it's very fitting that I came after Didier just now, because Didier and I were in that I think that was our first school together. And I'm always thrilled to be here, and so that's where we are. So today, I'm going to give you the first of 2 lectures on frustration and criticality in 2-dimensional Heisenberg antiferromagnets. That's a mouthful. So let me tell you what we're going to do first, and then we're going to do it. Okay, and please ask me lots of questions. Can you hear me in the back? Good. So our first lecture, great start, break the chalk. Okay, first lecture is going to be on frustration going to order. We all know what frustration means in everyday life, but what does it mean in the context of magnetic systems? Normally, we think of frustration as leading to chaos or disorder, but we're going to take our lemons and make lemonade. We're going to look at specific cases where frustration actually leads to order. Is that big enough? Can you see in the back? Is that good? Yes, good. Okay, let me know if you can't hear me, see me, understand me, whatever. Okay? So that's going to be today. And then on Tuesday, we're going to learn about how frustration can lead to criticality. Now, I realize that you all come from a wonderfully diverse set of places and come with a wonderfully diverse set of backgrounds. So the very first thing we're going to do today is we're going to unpack this title, okay? We're going to unpack this title. What are all these words mean? And then the second part, we're going to look at a very simple model and see how frustration and the fluctuations that are developed with frustration can actually lead to long-range order, because that's somewhat counterintuitive. So that's the plan. Let us begin. Okay, so magnets. Okay, you probably all have played with iron filings, iron magnets. Here we're going to focus on systems with well-defined local moments. That means that almost isolated ions with partially filled shells. And magnetism in general comes from Hund's rule. So for example, let's take manganese, which has this filled structure for SD5, and manganese 2+, so I take away 2 electrons, that means I have 5 left, and Hund's rules tell me that my spins are like this. Okay, and that leads to magnetism. Now, local atomic physics, namely spin-orbit coupling, crystal fields, the fact that there are electric charges around, lead to a wide and rich variety of magnetism. Okay? Yes? Manganese 2+. So manganese has 4s2d5, and so I take away 2 electrons, and so I have, if I take away 2 electrons, then I have 5 left. Pardon? Pardon? Yeah, these go. Okay? So that was just an example. That's, and actually you'll see it's relevant for the experiment we're going to talk about. Yes, I'm going to mostly be on the blackboard, but I'm going to show data from real experiment. By the way, between college and graduate school, I worked in a lab, so I have a very healthy feeling for experimentalists. I can take a laser apart. I used to know how to put one together again. So, I'm not sure if you want me in your lab. I follow directions very well, but I do not have magic fingers. Okay, so how do we experimentally identify it? Because that's, of course, very important. We want it to be electrically insulating. That's not to say there are not other kinds of magnets, but that's what we're interested in, which means that if we measure the resistivity, we should have some sort of gap over T. And what's very important is we should have a Curie susceptibility. I had the honor earlier, last month, in Paris to see some of the instruments that Marie and Pierre Curie actually used to measure the Curie susceptibility. The susceptibility is chi is limit as h goes to 0, m over h, and in a paramagnet, you get 1 over t behavior, as you know very well. Okay, so we can think of, let's think of a magnetic system. And if we look at the inverse of chi, since chi goes as 1 over t, we see that at high temperatures, it's like this. Then if we extrapolate down, it should extrapolate to t equals 0. Okay. All right, but of course, the magnets that we know the best are magnets like iron. So let's think about iron. In iron, we have ferromagnetism. Of course, ferro is iron. Ferromagnetism, which means we have something like this. And if we look at the inverse susceptibility, it does something like that. Okay? Now, let's talk about ferromagnetism. We have a magnetization, and the magnetization is the magnetic moment over V. And remember that the magnetic moment is defined through the energy. And it's the rate of change of energy with the applied field. Okay, why are you telling us this, you might say? Well, let's think about what happens. How do we get ferromagnetism? Okay, you might think, okay, remember iron was known long before the 20th century. You might think that you have electrons that are circulating and give you some magnetism. After all, we know from Ampere's law that if we have circulating currents, we have magnetism. But let's remind ourselves of something else. Let's remind ourselves of the Lorentz force. Lorentz force for a charge in a field, an electric field goes like QE, and a magnetic field is V cross B. Okay, that's a Lorentz force. But look at this. The force is perpendicular to the velocity, which means no work is done, which means that the energy cannot be a function of field, which means we can't have a magnetization. Another way of saying that is the fact that the rate of work would be F dot V, and that's QE dot V, and there's no B dependence because of this, and therefore E cannot be, this is energy of course, that. So no magnetization. But wait a minute. What about iron? What about diamagnets? What about paramagnets? What we've just realized, and this isn't often discussed, is that quantum mechanics is necessary for magnetism. Okay? If we didn't have quantum mechanics, we wouldn't have magnetism. We're often taught in school about the black body radiation, about the photoelectric effect. Those are all very nice. But without quantum mechanics, we couldn't explain iron. Okay? So it's very, very important. And I just remind you that from a formal standpoint, this is called the Bohr-van Leuven theorem. This was in Niels Bohr's thesis. And it was Hendrika Johanna van Leuven, her thesis in Leiden, Bohr's thesis in Copenhagen. And what they showed was there was no thermal equilibrium magnetization in a classical system. So let me just, I'm not going to go through the whole proof, but just let me give you the basic idea. This is the way I think of it, okay? But let me tell you the formal way you think of it, because it sort of relates to what we've been talking about before. Let's write down the partition function for n particles of charge q. So our partition function is going to be x to the minus, and now we'll have some energy. Beta is 1 over the temperature. This is the energy, and I'm going to have as a function of position and momentum. And then, of course, I have dr1 all the way to drn, dp1 all the way to dpn. So this is going to be a 6-dimensional phase space, 3n positions, 3n particles. But what we know, and we've already discussed earlier this week, is when we turn on a magnetic field, we basically take our momentum to P minus QA. Okay? We've been talking about Berry curvatures. This is the real vector potential. Okay? Now, when we do that, remember the limits of these integrals are just from minus infinity to infinity. So all we can do is shift. We can absorb this shift just by absorbing the origin of the momentum integration. And when we do that, of course, the partition function is not a function of B, and the free energy is not a function of B. Ergo, classically, we can have no magnetism. Okay? Now, it turns out that in astrophysics, they do get classical magnetism. And the reason is that they have additional terms here due to the fact that stars can rotate. If you allow the object where the electrons are running around to start rotating, then of course all bets are off with this. Okay? But here we've assumed that our solid is not going to rotate. It doesn't have additional degrees of freedom, and this is it. Okay? So one of the things I want to emphasize is that it's really important for magnetism to have quantum mechanics. In fact, it's interesting because Van Vleck was the first to popularize this in a 1932 book he wrote on electric and magnetic susceptibilities, and he called this work of Bohr and Van Leuven the most deflationary publication of all time. Because in 1932 he said, we have to find a way to understand diamagnetism, paramagnetism, and ferromagnetism. Okay? In those days, they didn't know about antiferromagnets. That's coming next. And he speculated that doing this may have contributed towards Bohr thinking about his semi-classical approach to the hydrogen atom. Yes?
So when you're writing P in that form,
Yes.
can be a function of P, right?
Pardon?
The vector potential can enter into the partition function.
Yes. So what I would, this would all go in here, but then because it goes from minus infinity to infinity, I'm being very impressionistic here, you can just shift your origin, and then it's absorbed. That's the point. And that's the basis of the Bohr. I mean, you can look it up. It's of course rigorous, but that's the basis of it. Now, there's a very nice argument by Stephen Blundell in his magnetism book, which I recommend for those of you interested in magnetism. And what he says is the following. He said, wait a minute. You might say, I know that an electron curves when I turn on a field, so I don't get it. And so he has a nice picture. So what he says is the following. He said, let's turn on a magnetic field, and let's assume that we get these orbital currents like this. A little bit like what we saw in Dima's talk yesterday, okay? However, we have these, what they call skipping orbits. That means that you have a surface that cuts off an orbit, and that's also going to be like this. And so what he's saying is, here we're going in this direction, here we're going in that direction, and that's how you get m equals 0. All right? So the take-home message here is, for magnetism, quantum mechanics is necessary. Okay. All right. Any questions? All right, next. Interactions between spins. So André already introduced us to the Heisenberg model, so let's write that down. The Heisenberg model is J, Sij, Si dot Sj. Okay? And here, J is less than 0 is ferromagnetic, and J is greater than 0 is antiferromagnet. Now, a brief history of antiferromagnetism. And André alluded to this in his first lecture, and I'm just going to talk about this a little bit. We had two giants here, Néel and Landau. As you know, an experimentalist and a theorist. Néel did some susceptibility measurements. So remember that we had chi inverse versus T. This is Curie. This is paramagnetic. This is ferromagnetic. But what Néel noticed was there were a number of materials where they extrapolated to some negative value, which we now call Curie-Weiss, and it went like that. Okay? So he postulated that you have a ground state like this. Okay? And he didn't have any proof, but he postulated that that's how he could explain the data. Okay? There's a problem here. And the problem is that this is not the ground state, strictly speaking, because M is not conserved. This sublattice magnetization, does not commute with the Hamiltonian. So this is not a conserved quantity. So Landau instead, being one of our amazing theorists, instead suggested that we have a singlet ground state. And he had in mind something like this: down, minus, down, up. And this, of course, Néel was doing his measurements on three-dimensional systems. Landau was fueled by history in the sense that, first of all, this commutes with the Hamiltonian, and second of all, Bethe had recently shown the community an exact solution of the spin equals a half antiferromagnetic chain, which had power law correlations, critical correlations. That's this criticality we're going to talk about next time. Okay? And so Landau said we have this one solution for 1D, where we have power law correlations. Philosophically, I believe that we should extend this to higher dimensions, and there's no long-range order. So we had beautiful symmetry arguments and an exact solution by the theorists. and we had intuition by an experimentalist. And then in 1951 came neutron scattering. Okay, Fabrizi, please. So, turns out it's for antiferromagnets, you have to probe 2-point correlation functions. And with neutrons, with neutrons, you can couple the magnetic moments of the neutrons to the magnetic moments of the electrons. Is that the right light?
No,
Pardon? Did I do the wrong light? Sorry. But it doesn't seem to be on. Okay, so there were neutron experiments that were done on, thank you. Oh, thanks. Manganese oxide, which has a sodium chloride structure. It should be coming on. And let me say, okay, so this is manganese oxide, an experimental verified antiferromagnet. So what they found was at 293 Kelvin, they had a lattice spacing of something like 4 angstroms. But as they went down in temperature, remember this is in K space, they have a lattice spacing of 8. So you have a doubling of the unit cell. Now when they did X-rays, the unit cell did not change. So the fact that the magnetic unit cell doubled, but the X-ray did not, indicated that in fact Nail was right. So this is a message to the theorists: keep close to experiment, because you can have the most beautiful arguments, but nature tells us. Pardon? The X-ray part. So what they did was, the X-ray tells you about the position of the atoms. So the X-ray is just asking you whether there's a structural transition. So the fact that the X-ray isn't actually here, this is neutrons. So the neutrons couple to the spin of the electrons. So the neutrons indicate that there's a doubling of the unit cell. But when they did X-ray, which is not here, they found that the actual positions didn't change. And so that meant that it was only the spin unit cell, magnetic unit cell that doubled. That's right. That's right. Okay. All right. Thank you. That's all for the moment. I was told to mostly do Blackboard. Can I bring this up? And should I turn this on? This requires a lot of... Okay, this requires a lot of coordination. They didn't teach us this in graduate school. Okay, so this is 1952. Clearly, I mean, Landau was one of our greatest theorists, but clearly the symmetry arguments were not all there was to it. So, 1952, enter Anderson and Kubo, okay? And they had, so the question was, how come we're seeing this Nail state, even though it's, the sublattice magnetization is not a conserved order parameter, so it doesn't have a right to be a ground state. So why? So what Anderson and Kubo did, and this is 1952, Anderson and Kubo, was they developed a semi-classical theory, okay? And basically it's an analogy with a quantum harmonic oscillator. They said we had to worry about 0-point fluctuations. Okay, so how does that work? 0-point fluctuations. So I think I have to go here. 0-point fluctuations. So what they said was, let's think of an antiferromagnet as semi-classical spins plus fluctuations. So what they're saying, I'm going to draw some pictures first, and then we'll talk about how to get to the results. So let's think of a spin like this, like that, And let's think about the fluctuations of this spin, okay? Since we know it's not the ground state, it has to have fluctuations. Now, let's assume, as we heard in Jean-Noël's talk, let's assume that that we have longitudinal and transverse degrees of freedom. And for example, if for example it fluctuates to here, then this will be our magnetization and will be reduced by that amount, okay? And similarly here, okay? So it'll be reduced. And what we're going to assume is that the longitudinal fluctuations are slow and that these transverse fluctuations are fast. That's what we're going to assume. Now, I think Sidney Coleman, the great quantum field theorist, said the job of every theorist seems to boil down to investigating the simple harmonic oscillator over and over again. So this is a good example of that. Since it's Friday afternoon and I don't think you want to do a lot of fancy Polyakov scaling, we're going to see this through the simple harmonic oscillator. I'm a great believer in always having an intuitive feeling for your results, and then of course you have to go through the actual calculation, particularly if you want real coefficients. Okay, so let's remind ourselves about the simple harmonic oscillator, and then we'll see about the Anderson-Kubo spin wave theory. In a simple harmonic oscillator, what we expect is that the potential energy for a classical system is roughly kT. K is Boltzmann constant, T is temperature, okay? Just very roughly. So that tells us that the amplitude goes like 1 over omega squared, okay? Now, if we're going to do this quantum mechanically, then we can do the same thing, but instead of kT, we have h bar omega. And in this case, so this is classical, in this case we have x squared goes as 1 over omega, okay? Good. Now let's look at what Anderson and Kubo did. What Anderson and Kubo did was essentially that. They looked at the reduction in the sublattice magnetization to order 1 over s, okay? So that's looking at the leading order terms in this fluctuation. And what they found then was that the change in magnetization went as some d dq. Here we have the Bose factor, because we have bosons, plus a half omega q. Now let's just look at the limits. When we're classical, which means that T is very large compared to any frequency in the problem, the magnetization goes as d dq. And when we're classical, the Bose function just looks at T over omega. So we have, this should be 1 over omega. T over omega cubed. And notice that that's basically the same thing as we have here. Yes?
I'm confused about this argument. I think I just missed a sentence. So in the first line, is that a classical expectation?
Yes, this is just classical. I'm just asking I'm being very impressionistic here. I'm asking if I wanted to guess what the average of this is, what the amplitude goes like, because that's essentially what we're doing in spin wave theory. What would it be classically? It goes like T over omega. Then I'm saying the same thing quantum mechanically. What would go as 1 over omega? I'm just looking at the two, I'm going to look at the two limits. Sorry if I want, thank you for asking. So what I'm looking at is we're not going to go through a whole, it's Friday afternoon, we're not going to go through a whole spin wave theory thing. What I'm going to explain to you, because remember, I'm still unpacking the title. What I want to explain to you is why we have 3D Nail antiferromagnets. And we're going to be interested in 2D. So let's get to that. So now I'm going to look at, so what I'm doing is I'm taking the two extreme limits, classical and quantum, okay? And I'm being extremely impressionistic. Okay, now here, it's when we're very low temperature, it's just this term. And so now we have d dq over omega. Okay? Now, so the point I wanted to make is it's basically the simple harmonic oscillator. Okay, now, let's ask about antiferromagnetism. If we ask about antiferromagnetism, in an antiferromagnet on a d-dimensional hypercube, omega q is linear. It goes like q. Okay? So what does that tell us? Well, if omega let's look at the classical case. Classical. If we look at the classical case, that tells us that the Néel is okay for d, or let's do quantum. Let's do t equals 0 first. That's easier. Let's do t equals 0. So at t equals 0, that's this one. So what we're looking at is dq over q. Here we're going to put this at q. And what we see right away is that the way we ask whether Néel order is good or not is if this diverges, then obviously Néel order is not good. Is there a question? Mark, do you have a question?
I'm just wondering, the omega, is that the frequency of your magnon, or?
This is the dispersion, yeah, of my I'm just looking at the dispersion. Yes?
No, the dispersion is not q squared.
For an antiferromagnet.
Oh, antifer, sorry, yeah, I was on the ferromagnet.
Yeah, antiferromagnet is Q. Yeah, so for an antiferromagnet is Q. We're going to talk about ferromagnets. So here at t equals 0, I'm going to look at this. You notice that dq over q, if d equals 1, it diverges. That's good news because beta told us we have no antiferromagnet. So the way all we're looking for is divergences, okay? If it diverges, that tells us Néel is out. If it doesn't diverge, and we don't know what it is, but we just say Néel is out. If it doesn't diverge, that means the fluctuations are small, and therefore the Néel state is preserved. So for t equals 0, we have Néel for d greater or equal to 2, but not d equals 1. So that was very good because beta showed that it doesn't exist. And for t not equal to 0, we have this. Now for t not equal to 0, you notice that for d equals 2, we still have a problem. It's only good for d equals 3. Okay, so for t not equal to 0, Néel order is good for d greater or equal to 3. Okay, so, and what's even better is the magnesium oxide that we just showed, it had a reduction in its magnetization compared to what you'd expect, and that reduction was in very good agreement with what they calculated with this 0-point fluctuation treatment. Yes? No, never say that, but what...
My question is that when we want to start at the very beginning, we start with speaking about the fluctuations of the spin. And so what happens to the discrete behavior of the spin? Do we accept all the continuous amounts of the spin?
So, okay, so in order to do spin wave theory, you have to postulate a state and look at fluctuations around it. Okay, so I'm talking about, we're not yet at frustration where you have many different states, and that's actually one of the challenges. How do you actually do spin wave theory if you don't know what the possible ground states are? But right now we're talking about systems where the neutron scattering has told us we have this ground state. Can we look at, we know that there are fluctuations because it's not a conserved order parameter, but how big are those fluctuations? That's the idea. Does that make sense? So what this is telling us is, so remember we had, for example, we had a spin like this, and we're looking at how far it goes over here, okay? So when it gets to here, if I can draw, the magnetization is going to be smaller than it was originally. So the reduction in magnetization is due to this, but if it went all the way to here, I'd have nothing at all. So I'm assuming that the longitudinal modes are slow compared to these transverse modes. So I'm assuming a ground state and asking how unstable is it? And what we've shown here is that for d greater than 3 at finite temperatures, the Néel order is stable. That means the fluctuations are small. But for t equals 0, the fluctuations are small for d greater or equal to 2. So does that answer your question?
Well, yes and no. Yes, if I accept that it can sweep all the character, yeah, that is fine.
Yeah.
If I don't accept that, the spin gets all those amounts in between and it does not behave discretely.
Yeah, these are Heisenberg spins. But a good question associated with what you're asking is, how do we know, and this will come in with the experiments that I'll get to, that we don't have anisotropy that really means that it's continuous. Here I'm assuming it's perfectly continuous, which I think for manganese oxide is okay. Okay? But I understand that's a very good point. There's no anisotropy in this system put in, and really you could have anisotropy. Okay, are there any other questions? Okay, so I mentioned that neutrons are in excellent agreement with this, and now we're just going to do something which we're going to need later. We're going to be studying two-dimensional Heisenberg antiferromagnets. And you see, in 2 dimensions, at t equals 0, we have a Néel state, but at finite temperatures, we don't. Okay? So, before going any further, let's think a little bit 2D antiferromagnet. And here we're always Heisenberg. T equals 0, we have long-range order, but finite temperature. And if we have no long-range order, that means we have a finite correlation length. We have exponential correlations. The spins have a rigidity up to some correlation length, and then they decay. So let's just see if with dimensional analysis we can figure out how this goes. We know that at t equals 0 we have to have long-range order. So we know this has to go like some lattice spacing because it's a length. Now we have exp, and we know it has to go as some 1 over t because it has to go, the correlation length has to diverge as we get to t equals 0. We have long-range order. We know this has to be dimensionless, so we have an energy in the problem, which is Js squared. And then it turns out if you do a lot of calculation, which we're not going to do today, but if you do Polyakov scaling or a renormalization group or whatever you want, you get a 2 pi. Okay? So the point that I want to, and we'll need this later on, which is why I am putting it here. So this is an exponential correlation length at t equals 0. Okay, so we're still unpacking. Frustration. Okay, we all know what frustration means, but what does it mean in the context of spins? We already learned a little bit about this from André. Can anyone tell me a spin system that's frustrated? I noticed you have many posters of frustrated system. What's the simplest frustrated system? Triangular, very good. The triangular Ising system, for those of you who aren't familiar with it, if you have an Ising system that's just up or just down, completely discrete, and we're all antiferromagnetic, this poor spin is confused. Okay? So what this means is that for every plaquette, you have a bad bond. Okay? Not all terms in the Hamiltonian are satisfied. We have one bad bond per plaquette, and there are many, many ways of tiling the two-dimensional plane. Okay, so there's a story here. Wanye, Gregory Wanye, who may know from Wanye wave packets, he was starting at Bell Labs. He was someone who had worked on a lot of exactly solvable problems, and he decided that he wanted to use some of the techniques of Onsager to see if he could calculate the configurational entropy, that is how many states you have at t equals 0. Conyers Herring, who was a great physicist and also a great organizer, he was in charge of Bell Labs at that time. And he put Phil Anderson in the office with Wanye. Now, Phil is very phenomenological. He isn't as precise, but he always has some way of getting to the right answer, whatever. So the story is that Wanye came in one day, and on the blackboard was this picture. Remember, Wanye was working really hard with his transfer matrices and all of this stuff to try and understand what the entropy was. And Phil drew this picture. On the blackboard. Let's see, this is now you'll notice that here, this spin and this spin, I have 2 ferromagnetic, I have 3 ferromagnetic, I have 2 antiferromagnetic bonds, 2 antiferromagnetic bonds, like this. So this poor guy doesn't quite down, up, yeah, this is right. This poor guy doesn't know what to do because he should be up for this one and down for that one, okay? And similarly, this one doesn't know what to do. And so what Phil did was he drew these circles like this. And though this isn't an ordered state, there is some ordering to it. And he said to Wanye, I know that there's a lower bound on your entropy. It's KB over 3. This is entropy per site, log 2. And how do you get that? Because this has a log 2 entropy, and it's every third site. Now, poor Wanye went through all of his calculations, and he got 0.323 KB. Remember, this is 0.6. So that means that this state is a significant proportion of thing. Now, the key thing I want to say about this is that here you notice that we have spins that can be up or down, okay? We also have a large ground state degeneracy, obviously, because, and we have an extensive entropy, okay? Large ground state degeneracies are hallmarks of frustrated magnetism. There are no energy scales, there are many instabilities, and I like to think of them as economy strongly correlated systems, because when you have large grounds and large degeneracies and many instabilities, you can get very rich phases. Okay? All right. I think we've unpacked the title. Are there any questions? Are we good on all this? Because now I'd like to switch gears a little bit and talk about a very simple model, which is going to tell you about how we can get order from a frustrated system. Are you ready to go? How come there are no more questions? Okay, we'll keep on going. There'll be questions. Okay, so now I'm going to tell you about a very simple but frustrated model. And this is to let you see how fluctuations can actually select order. Okay, you could see a little bit in that Ising example where we had we have a large degeneracy, but there was some sort of funny ordering. Okay, we're going to see more of that. Okay, so let's take. Now we're in the second part. We're going to take the simple but frustrated model. Can you read my handwriting? You can blame my French school if you can't. I learned to write. I had to write cursive in CZM here, so. Okay. So we're going to have a Hamiltonian, which is now we're going to have two parts, all Heisenberg. We have a nearest neighbor and a next nearest neighbor. Okay, André already talked about this system it's a J1, J2 model. André talked about this system on the triangular lattice. We're going to be even simpler. We're going to talk about this system on the square lattice. So what we're interested in is here, this is J1, and then J2. Okay, so first, so we have J1 and J2, nearest neighbor and next nearest neighbor, all spins are Heisenberg. So the first thing to do is to look classically. Let's look when J1 is very large. So this term dominates. If we look classically when this term dominates, what we find is E is equal to S squared minus 2J1 plus 2J2. This guy wins, and so we end up with spins that are in a nail state. Okay? And of course, these perturb it, but they're basically in a nail state. Okay. The situation gets a little bit more interesting when we look at J2 large. When J2 is much, much less than J1, then we have E, that's energy, is S squared. We have minus J2 plus, so what we have, let's draw it this way. Okay, so now this is J2 and this is J1. Okay, I'm looking at when these diagonals are predominant. So we have plus 2J1 cosine theta. Let me just write this out and then we'll talk about it. Minus cosine theta minus J2. What we find is that these terms cancel. What does that mean? What this means is that if I put, let's say I put up, down, like this spin is a little bit like those flippable spins we saw in the Ising case. This has 2 up and 2 down. So the local field on this is completely 0. Okay? So you notice that J1 doesn't enter in this at all. These are completely, classically, they are completely independent. Those two nail sublattices don't talk to each other at all. So the sublattices, classically, the sublattices are decoupled. Okay? So classically, they're completely decoupled. And in fact, I have what we call an accidental soft mode because I have this degeneracy. I can move them back and forth. They're completely decoupled. Now, it turns out that these fields will introduce these spins will introduce a transverse fluctuation field and a fluctuation vice field. And what we'll see is that the spins actually like to align their fluctuation vice field to their easy plane. Now that's maybe a lot to say, so let's just go through how that works. Okay? This is something called order from disorder. We have classically a large degeneracy, but it turns out that fluctuations select states. Okay, remember that free energy is U minus Ts. At finite temperatures, the fluctuations select the states with the highest entropy. So let's have a sense of how that works within spin wave theory. So within spin wave theory, and I'm just going to outline the calculation. What we do is we take a spin, we ask this spin in the middle. We do spin wave theory assuming any angles here. And what we find is we find that it goes some function of qx, qy, and theta. Then what we're interested in is the free energy as a function of theta. We solve with spin wave theory for this, and then we put it into the free energy, which, since omega should be small, we can linearize. Usually this is sinh, but what we're going to do here is linearize sinh, so we have just this. And what we find at the end is that the change in free energy as a result of angle, where the free energy, this is F theta minus F, is actually a function. It's some E of t, which we're not going to worry about. It's a function of 1 plus cosine squared theta. So, and this all assumes that, I should say, this all assumes that J2 is much, much greater than J1. So in other words, what we find in this, pictorially, is that when we look at the fluctuations, they prefer to have two states like this. So what we get is we have two states, one that's ferromagnetic in the x direction, and the other that's ferromagnetic in the y direction. So here we have the possibility, I just finished, then I'll get to, here we have the possibility of any, what I'm doing here is looking at this and this, that's this. Here we have the possibility classically of any angle, but then when we look at the fluctuations select the states that are parallel or anti-parallel. And a way of seeing that, I'll get to in a moment, Miska, just hang on please, is that ferromagnets, as Mark mentioned, go like Q squared. That's soft. Antiferromagnets go as Q. So here we're maximizing the softness by, in one direction being ferromagnetic, in the other direction being antiferromagnetic. So these two states, there's a ground state degeneracy, but the fluctuations select two states from the ground state degeneracy. Sorry, go ahead, Priska.
Is there a signer in this form?
Yeah, it should be minus this way. Well, this should be, there's a minus sign here in front, sorry. No, well, it wasn't very evident, but thank you. And I make lots of mistakes, so you're completely right, but there's a minus sign here. Now are we good? Yeah, that's fine. Yeah, that's fine then. Okay, so the point is that two states are selected from a whole degeneracy of states, two states. Okay, and again, now the interesting thing about this is that normally in magnetism, we describe magnetic behavior by long range, what we call an action, where we take gradient of the order parameter and all of this. But you notice that here the fluctuations have broken the lattice symmetry. Okay, this is an interesting effect. It's the little guys that are doing all this. Okay, it's a short wavelength fluctuations that are breaking the lattice symmetry. We started with a Z4 symmetry. We don't have that anymore because ferromagnetic is in the x direction or in the y direction. Okay, so what spin wave theory does is it actually is able to capture these short wavelength fluctuations, which in this case break the symmetry. Okay, so now what happens with all of this? One of the questions is, can we see this experimentally? And for that, I would like your assistance, Fabrizi. So experimentally, this has been observed. This is something called order by disorder. Okay, I'll write the references in a minute. This is something called order by disorder. I should put the references. It was first discussed in Leningrad by Shendar in '77. it's first discussed in Grenoble by Villain in 77. Then it was discussed by Chandra independently in Leningrad. And finally, Chris Henley was the one who thought about it for Heisenberg systems. Okay, it should come on. So what people do to see order from disorder is that they check. I mentioned that you have these classic degeneracies. So you have these classic degeneracies which lead, which lead to unexpected gaps, unexpected zero modes, okay? But these zero modes are going, and so what you can ask then is, for a system with finite S, because this is spin wave theory with S, do we have interesting gaps that can be calculated using this order by disorder? And so what this group, this is Chandra and a group in Grenoble, what they did was they looked at a garnet system, and what they looked at was the distinction in their particular structure, which I'm not going to go through. They looked at the mode that was in phase and the mode that was out of phase. And to show that order from disorder was selecting a state, they should see a gapless behavior for the in phase and gapped behavior for the out of phase. And that's what they claim. This is the gapped behavior, and they claim that this gap they can explain with their spin wave theory. They go to higher order than what we're talking about. They go to second order, okay? It goes like square root of S then. They're able to explain it. And they see this coming sharply down, and this is the mode where they're together, okay? Now, this was first in 1988. Could I have the next one, please? Thank you. There was some controversy because there was an issue about whether or not it could be explained exactly as we were talking just now with anisotropy, not necessarily order from disorder. This is a more recent one. Both Lucille and Leon will be here next week, so if you have questions about it, you can ask them. This was an XY pyrochlore system where they went to the researchers went to great effort using inelastic neutron scattering to confirm the form of the Hamiltonian, and this is what they got. So I just want to say that experimentally, this has been seen. Okay, thank you.
Can you explain like on 5 what that's supposed to be?
Pardon?
Can you just like explain like on 5? I might be the only person.
No, please. What did you want me to explain?
The stuff that you were writing on the board earlier.
Okay, let's...
Kind of what that theory does and how it relates to the line that you were writing.
Okay, well, I'll tell you what. I'm going to do a little bit more, and then we'll get to that. Can I get to that in a moment? All that I wanted to show was that you have a gap, and I'm going to talk a little bit about length scales, and then I'll get back to your question. Promise. So I'm going to do something with length scales, and then I'll get back to exactly that, okay? I should say theirs is for a much more complicated system than this. Okay, I'm doing a much simpler structure. Okay, and theirs is in 3D, and I'm just in 2D. All right, so we talked about this. We talked about, and we do have some sort of order parameter. We have an order parameter associated with a 4-spin order parameter. We have an order parameter which is S1 minus S3 dot S2 minus S4, something like this over S squared. And that's basically saying we can think of this as being plus and this as being minus, okay? Now, remember, oh, I've already erased it, but remember, oh, here, it's here. Remember that a 2D antiferromagnet at finite temperatures has a finite correlation length, okay? But now we're going to be bold. We're going to say, look, I can define an Ising type, it's really Z2, a Z2 order parameter. I call it Z2 because I don't break time reversal symmetry. A Z2 order parameter, plus and minus. Do I have a chance of that order parameter existing at finite temperatures? And I know that I can't have 2D Néel order at finite temperatures, but what about discrete order? And so that's going to be the question. What happens? What's the phase behavior? So what we're going to ask is the following. Let's just take these two right here, okay? And we're going to say, suppose I have down and down, or maybe it's not, okay, maybe it's those two and these two, okay? And suppose I have down and up, okay? This one, if I want to go from one to the other, this one stays the same, but this has to rotate, okay? And that's what we usually call a domain wall. In an Ising system, we can have two kinds of domains. We have a domain wall within them. Now, what we're going to argue, you can do a full renormalization group calculation, but I'm not going to do that Friday afternoon. But what we're going to argue is, if we can find when the nail correlation length is greater than the width of this domain wall, then we can say we have Z2 order. But we know that at higher temperatures, this is getting shorter and shorter. Okay? So if we can define a domain wall such that the spin correlation length is longer than that, then we're good. Okay? So that's going to be our estimate. And amazingly enough, it turns out that it does pretty well compared to the full RG treatment. So how do we already know what psi is. That's why we pulled it out before. Now, how do we get the domain wall? So the domain wall, what we can say is our action is going to be, and here I'm going to be very impressionistic, we're going to have some J2 term for our main bonds, and then we have another term, and this is due to this order from disorder. And I should say that this has to be put in by hand. This comes from spin wave theory. This is our cosine square term. Now you can ask, what's this term? Well, the fluctuation term goes something like psi times, so we're going to have the fluctuation vice field times the susceptibility. This goes as 1 over J2. This goes as J1 squared. So what that tells us is that the energy of a domain wall over A goes something like J2 over, I'm just going to call it W, plus J1 squared over J2W over A squared. Okay, so how do we get a domain wall out of that? Well, we minimize this energy of the domain wall, and when we do that, we get minus J2 over W squared plus J1 squared over J2A squared equals 0, and what we get out of that is that W equals J2 over J1A. Okay? So, what we've gotten out of all of this is, if we put all this together, the condition for the stability of the Z2 order is, we're going to equate this. So we're going to say when psi is of order W, so that's e to the 2 pi, which we got from our renormalization group. Tc is equal to J2 over J1. And what we get out of this is that Tc is, I'm not going to put in the 2 pi's because we don't have that kind of accuracy. But what we do have is J2S squared over log J2 over J1. And you notice that if J1 is 0, then Tc goes to 0. Okay? So what this is telling us is that even though we have no long-range nail order. The fluctuations are leading to a discrete symmetry breaking and a Z2 ordering. Okay? Now, I was asked before about the gaps. So in this system, we would have our usual gaps. This is the Brouillon zone. Here we would expect at finite temperature a gap that goes as the speed of sound over psi. Here we would have one that goes as the speed of sound over psi. This is 0, 0. This is pi, pi. That's what we expect for an antiferromagnet. However, we also have these gaps associated with order from disorder. And then this length scale that we have, W, this would be a gap C over W. This would be a gap C over W. And it's exactly those gaps that they calculated before. So what they were looking at was they were looking at here and here before, but in the equivalent in their structure, which is much more complicated. Does that make sense? So in an antiferromagnet, we expect at 0, 0, and pi, pi to have Goldstone modes. But the point is here we have additional degeneracies associated with the fact that you can turn these spins. You can, they don't know each other. And so the order from disorder gaps are here. And they actually showed that those gaps go as, I'm being very impressionistic here. They showed that, I mean, they did a real calculation, showed that to second order in perturbation theory, it goes like square root of S, and they were able to get this very nicely. And they showed that these gaps change differently than these do at the temperature they were able to measure. So does that answer your question? Okay, say it again then, sorry.
I was asking about the step-by-step, just explain to me like on 5 what the whole spin wave theory, how that relates to every single stuff.
Okay, so in,
In the first two sets, you drew a lattice and then you drew a different lattice. The lattice looked different.
oh, so what I did was, okay, first of all, so let's go back. Spin wave theory, the idea is that I have these spins like this, but now I'm going to look at fluctuations about those spins. And I'm going to ask a little bit like you may know from Ginsburg criteria, I'm going to ask, are those fluctuations so large that I can no longer think about these spins like that? So if I'm fluctuating like crazy, are the fluctuations small? Okay, so what I was looking at before, spin wave theory says, let me ask how large the fluctuations are about that. So all that I did there was to show when they diverge, obviously you can't do this. Okay, now, when I drew the lattice in two different ways, the idea was that originally I drew it like this, and this is emphasizing the J1. So J1, J1, and this is J2. But instead, what I can do is draw it like this. Those are just the dotted lines. And now I can turn it around and say J2 is much bigger. You see, all I'm doing is taking this diamond here. And now this is much bigger. And so that was all I was doing. The one that I was drawing this way is when these bonds are bigger, and here these bonds are bigger. Does that make sense? Sort of? Is that better? Maybe we can talk offline a little bit more. Okay, and so here what I wanted to do is to say that here I expect gaps, but in this case, the gaps will just go as 1 over the correlation length. Whereas in these cases, the gap will go as 1 over the domain with size. And so that's what's going on there. Are we good on that? Okay. Any other questions? Yes, go ahead. Oh, all I was saying was that this is where we would have our gaps. This is just a Brouillon zone. And I was just saying that this is 0, 0, 0 pi, 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 and 0, and pi 0. So nothing fancy. And again, the Brouillon zone for the structure they looked at is much more complicated than this, because it was much more it was a body-centered tetragonal system, so much more complicated. But I'm just giving you a feeling for how this works, hopefully. Before I tell you about numerics, is there anything else? Is there anyone else? Yes.
So before you show some neutron scattering data of this,
Pardon?
you show some neutron
Yes. And so they're picking this, in those cases, they're looking at a more, I mean, it's a more complicated than this. But say, are we fine? Okay.
Now in your
Pocket, thank you. Okay, now we can ask, how are we for time? Okay, could I please have the slides now? Now what we can do is ask, you know, everything that I've done assumes that we have a second order transition, and it doesn't always work that way. So we have to do some numerics, okay? Now, it took a long time for the numerics to be done because here the domains are very large. Do I turn off this light? Okay, we're getting just in time, we're learning the system. Okay, so I think it's going to come on. What you'll see on the right, once it arrives, is the phase diagram. The phase diagram is at the high temperatures, of course, we have no ordering at all. Then there'll be, is it coming? Aha, thank you. So at high temperatures, we have no ordering at all. Then sorry, J1 and J2 are in the wrong direction here. Okay, then we have decoupled sublattices. Sorry, J1 and J2 are reversed, but okay. You see, this is J1 here, and this is J2. So let's say, take J1 is the bigger one, okay? So we have free moments here. Now we're going down in temperature. Then there's going to be some temperature where we have completely decoupled sublattices. And here there's going to be some Z2 transition where we get a Ising type transition, okay? And all the way down, we'll get then Ising Z2 order. So that's what we're after, okay? Now, it took a while, but in 2003, there was computational confirmation from Cedric Weber and Freddy Mila. This is susceptibility, and this is the correlation length. The good news is, A, they saw the transition, and B, it's not first order, okay? And it seems to have the exponents of the Ising, okay? All right. Then, could I have the next one, please? The Monte Carlo phase diagram. One of the points was that in our calculations, we had to take J2 to be extremely large compared to J1. So the question is what happens when it's not so large, and we were able to look back there. They're able to look much closer, and it seems like it works reasonably well. So that's good news. Okay, but this is all very nice, but is there some link to experiment? And that wasn't obvious for a long time, but then came the iron pnictides. And can you please show me? You're going to hear much more about these from Amalia. I won't say a lot, except that in the iron pnictide systems, in some of them, one has an antiferromagnet, one has an orthorhombic transition, a tetragonal phase. You might, at first glance, think that this is a structural transition that drives the antiferromagnetism, but many believe that it's actually the antiferromagnetism that drives the orthorhombic transition. Could you have the next one, please? Indeed, the pneumatic transition is now called pneumatic, this D2. The pneumatic transition seems to coincide with the orthorhombic transition. People found that if they did density functional theory and they didn't set the spins to be antiferromagnetic, they couldn't get the structural transition. The spin structure from neutron scattering suggests that one has this 0 pi pi 0 kind of behavior that we've just been talking about, and this led a couple of different research groups to suggest that one had a J1, J2 model. Of course, with iron, it's a little tricky because it's sort of in between being local moment and being itinerant, so that's a whole tricky issue. And of course, our model was a local moment model. So could I have the next one, please? Others were able to understand this using a more itinerant approach. I focused on local moment magnetism. Of course, there's also itinerant magnetism, so there was some possibility of that. So one of the ideas was, and could I have the next slide too? How would you actually probe, thank you, a four-spin correlation function? You can't do that with neutron scattering. Neutrons can probe a two-spin correlation function, but not a four-spin correlation function. So one of the ideas was to ask whether elastic degrees of freedom would couple to a four-point correlation function. And to make a long story short, one can look at shear, and the idea would be that the antiferromagnetic bonds are longer than the ferromagnetic bonds, or maybe it's vice versa, I can't remember which way, but there's a different length in bonding, and that's what would then lead to this orthorhombic case. You can do a quick calculation of the, if you assume a very simple linear coupling, magnetoelastic coupling, you can look at the renormalization of the shear modulus, and you can show how it's related to this pneumatic susceptibility. And could I have the next one, please? And what comes across is, if you look at resonant ultrasound spectroscopy, there's pretty good agreement for these two systems. So what it suggests is that pneumatic fluctuations are low energy excitations over a very broad energy temperature range. But of course, the big question, which I certainly can't address, is how important they are for the superconductivity. Okay, thank you. I won't have any more slides. I'm just going to try and wrap up now. Oh, do I turn on this light? Do I turn this? So the iron pnictides were an unexpected possible connection with experiment in all of this. So order from disorder. And I didn't get a chance to write it. Villa is 77. Then there's Shandar and Henley also. And I can give you the references if you're interested. The key point is that and we're talking about classical, is that we have a free energy that is E minus Ts, and that the entropy weight leads to ground state selection from each dynamical manifold. Fluctuations lead to an ordered state, and that's what's really crucial in all of this. I should say that order from disorder is also why it's so difficult to get a spin liquid. Okay, Lucille's going to talk about spin liquids next week, because order from disorder, if you have a large ground state degeneracy, order from disorder usually selects an ordered state. Now, how can we get around this? Well, the entropy can be thought of as having two parts. We can talk about the continuous fluctuations, and that's in some sense what we've been talking about today. This is the order by disorder. And then you can think about the configurational entropy, and that's the discrete entropy. Okay, that's discrete. Now, usually, S theta is larger than SD. Usually, S theta is larger than SD. And this is SD is very difficult to determine analytically, okay? However, exact enumeration is allowed in recursive structures, okay? So a recursive structure might be like a Hasumi cactus. It's like a beta lattice, but instead of, you have polygons instead of sites, okay? So the Hasumi cactus. And you can actually calculate it. And in fact, there are special systems where you can calculate this SD, and you can actually show that you can get this to win. I should say that this SD is a little bit, if we think about electronic propagation in disordered media, SD is a little bit like a delocalization bandwidth. This term wants the system to just flow along, so a delocalization bandwidth. And S theta can be thought of as some sort of RMS of a random potential, inhibiting diffusion. And you may be familiar with the delocalization criteria. If you have a random potential, the delocalization criteria, that is when you actually get the electron to diffuse around, is that the bandwidth has to be larger than dVr squared. And here the key thing is that S theta scales with n, okay? Because every spin has some continuous fluctuations. In order for this to even be competitive, it has to scale with n, and then you have to figure out numbers matter. So in this these kinds of recursive structures you can calculate, but it's really hard to get around order from disorder, okay? Now, I should say that unlike in the delocalization condition, entropy doesn't have a time scale. So even if you do have SD greater than S theta, okay, you don't know whether you have a liquid or a glass. We don't know about the dynamics. That involves the barriers, okay? So I hope I've given you a sense of fluctuations and how they can lead to discrete order, okay? We talked about how we unpacked the title, then we looked at a simple model and talked about how in this simple model, fluctuations, in this case thermal fluctuations, actually selected a Z2 discrete order that, despite the fact that the background was disordered, we ended up having a discrete order parameter composed of relative spins, okay, that persisted to finite temperatures. It was confirmed by numerics. Now, the next time, we're going to talk about how fluctuations can lead to power law order. Now, power law order is criticality. You might think, wait a minute, I think of XY magnets, criticality, that's Kosterlitz-Thales transition. We heard that in 2D Heisenberg antiferromagnets, we have homotopically stable vortices, but they can't bind because we have a finite correlation length. So why am I going to talk about criticality? Well, stay tuned, come back on Tuesday, and you'll find out. Thank you. And I should also thank Fabrizi. Thank you, Fabrizi. I need all the assistance I can get. Are there any questions? I'm happy to, I'll be around for the next week, so I'm happy to answer. Yes.
I have just one question.
Yes.
Concerning, there's always the search for a true spin liquid
Yes.
at low temperatures. And usually, disorder from disorder prevents it.
Exactly.
So because, you always get back a little bit into disordered states.
That's right.
So does that mean, in order to have a true spin liquid state, that we need to look for systems where indeed the delocalization entropy or
This is very large. Well, of course, I think, Lucille will be talking about that, but of course, when you get into the quantum systems, everything I've talked about is classical. But it's very difficult, yes, it's very difficult to go against order by disorder. And so in some sense, I'm the warm-up band for Lucille because I want to say how hard it is. The other thing that's difficult about a spin liquid is that you really have to make sure that you don't have higher order correlations that order.
sure.
Okay?
It's always the question of how to identify.
Yes, multipolar order, all of that. But absolutely. Certainly for these classical kinds of things, it's tough to beat. It's really tough to beat. Okay. Thank you, everyone.